Life cycle assessments serve as tools to evaluate the environmental impact of human developed technologies and systems. Unfortunately, even the most comprehensive and meticulously conducted LCAs carry some degree of uncertainty. These inherent uncertainties characterize many actions undertaken to enhance environmental quality. So, how can we determine with greater certainty which actions effectively reduce environmental impact? An environmental performance indicator, EPI, is a standardized measure that quantifies the environmental impact of an organization, product, process, or activity, providing a clear and measurable assessment of its sustainability and environmental responsibility. And LCA, on the other hand, is focused more on the material and energy input and output at different stages. This does not necessarily capture the environmental effect of those required inputs or resulting outputs. So, again, environmental performance indicators are crucial tools for assessing the effectiveness of environmental actions and initiatives. These indicators provide valuable insights into the progress and success of various environmental programs, ranging from individual efforts to nationwide campaigns. EPIs encompass a wide range of environmental issues, including monitoring the levels of pollutants in air, water, and soil, assessing the health and diversity of ecosystems, evaluating greenhouse gas emissions and climate change impacts, tracking energy consumption and efficiency, monitoring soil erosion and land degradation, assessing the benefits provided by industry ecosystems such as clean water and air. But not all EPIs are useful in all scenarios due to the diversity of environmental problems. For example, the use of a new genetically engineered corn may have little bearing on the level of deforestation in the upper taiga of Canada. To be useful, EPIs should indicate whether the state of the environment is changed positively or negatively and provide a measure of that change. Also, EPIs are more meaningful if they quantify the results, allowing for comparison between the impact of different types of pro environmental actions. EPIs can be categorized into four main types: inputs, outputs, outcomes, and impacts. Each type plays a distinct role in assessing the overall environmental performance of an activity or process. Inputs represent the natural resources of ecosystem services that are consumed by an activity to produce a particular output. These inputs form the foundation of the production process and can include raw materials, energy sources, and water resources. By tracking the quantity and quality of inputs, we can gain insights into the environmental footprint of an activity at its earliest stages. Outputs are the tangible goods or services that result from an activity. They represent the direct products of the production process and can include manufactured goods, electricity, or waste materials. Measuring and evaluating outputs provides a direct assessment of the tangible outcomes of an activity, allowing us to identify potential environmental impacts and resource inefficiencies. Outcomes encompass the broader environmental, social, and economic consequences of an activity. They extend beyond the immediate outputs and capture the wider implications of the activity on the environment and society. Outcomes can include improved air quality, increased employment, or enhanced biodiversity. Assessing outcomes provides a more holistic understanding of the overall impact of an activity and its contribution to sustainable development. Impacts represent the longer term and more extensive consequences of an activity's outcomes and outputs. They reflect the cumulative and indirect effects of the activity on the environment and society. Impacts can include climate change, resource depletion, or social inequality. Evaluating impacts provides a comprehensive assessment of the long term environmental and social ramifications of an activity, allowing us to make informed decisions about sustainable practices. To illustrate the concept of environmental performance indicators, let's consider the example of electricity generation from coal. In this scenario, coal serves as the input for the electricity generating plant, representing the natural resource consumed to produce the desired output. So, coal is the primary input for the electricity generating plant. It is a fossil fuel that undergoes combustion to release heat, which is then converted into electricity. Electricity is a tangible output of the electricity generating plant. It is a form of energy that powers various devices and appliances in our homes and businesses. And the ability to read at night is one of the positive outcomes of electricity generation. Electricity allows us to illuminate our homes and workplaces, enabling us to engage in activities like reading and studying even after dark. However, visible air pollution is an undesirable outcome of electricity generation from coal. The combustion of coal releases pollutants in the atmosphere, contributing to air quality degradation and respiratory health issues. The potential for a better educated person is a positive impact of electricity generation. Access to electricity enables individuals to pursue education and knowledge acquisition, potentially leading to better career opportunities and overall well being. Conversely, increased potential for global climate change is a negative impact of electricity generation from coal. The combustion of coal releases greenhouse gas emissions, primarily carbon dioxide, which contribute to the warming of the Earth's climate. Evaluating the effectiveness and relevance of EPIs involves a careful examination of each indicator and its relationship to the activity being assessed. If you were called upon to perform an EPI, you should inquire about the following. Is the input, such as coal in the electricity generation example, an appropriate choice for the activity? Are there alternative inputs that could be used with less environmental impact? Is there enough of the input available to sustain the activity over time? Are there concerns about resource scarcity or depletion of the input? Are there any potential problems or disruptions that could interrupt continued access to the input? Political instability, social unrest, or environmental factors that could impact the availability of the input. Does the output, such as electricity, sufficiently address the problem it is intended to solve? Does it meet the need and demands of the users? Is the output produced and delivered in a timely manner to meet the needs of the users? Are there any delays or bottlenecks in the production process? Does the output create the desired outcome, such as the ability to read at night? Does it fulfill the intended purpose of the activity? Does the output also result in unwanted outcomes, such as air pollution from coal combustion? Are there any negative consequences associated with the production or use of the output? And finally, do the outcomes, such as the potential for a better educated person and increased global climate change potential, result in long term impacts that are widespread? Are there any significant and lasting effects of the environment and society? By carefully considering these questions, we can assess the strengths and limitations of EPIs and their sustainability for evaluating the environmental performance of various activities. Understanding the value of environmental performance indicators. The effectiveness of environmental performance indicators hinges on the collection and analysis of diverse data sources. A singular application of an API often provides limited insights, necessitating a broader context for meaningful interpretation. To fully grasp the significance of API findings, additional data sets are crucial. Types of additional data for API interpretation include absolute values. These values represent the total data collected for a specific question. For instance, comparing the total recycling impact of a city with that of other cities can provide a more comprehensive understanding um, to its performance. Additionally, evaluating the overall cost of a recycling program against its absolute impact offers a broader perspective. Normalized values are values represented by data calculated on a per X basis. So, comparing recycling rates per person between cities, countries, or businesses can provide valuable insights into relative performance. Similarly, analyzing the amount of aluminum recycled per dollar spent on recycling can assess the cost effectiveness of recycling initiatives. Or examining the amount of waste recycled per certain quantity might be useful as well. And lastly, trends. Trends represent the changes in data over time. In the example from our textbook, we can see the municipal solid waste, or MSW, recycling rates in the United States from 1960 to 2015. On the x-axis is the time frame, and on the y-axis we have data sets plotted. Both of the lines provide trends, which allow us to see the change over time. In blue triangles are the total MSW that is recycled or composted. This provides us with absolute values, and we can use this to compare how the US has done in total tonnage recycled and composted in the past through 2015. In addition, the second data set plotted on the y-axis, as indicated with the orange boxes, shows the percent recycled. Percent is a normalized data set. What a percent means is how many parts per 100, or on a per 100 tons basis. This allows us to actually see that 91.2 tons is roughly 34.7% of the total generated municipal waste. From here, we can reference our questions we can use to evaluate this set of EPIs. Does the output of recycling municipal solid waste sufficiently address the problem? Or does the output create the desired outcome? Or how about, does the output also result in unwanted outcomes? We can see that if we only had the absolute data in tons of municipal waste recycled or composted, it would be impossible to approach useful conclusions to these questions. And so our trends, um, as well as if we go back here to the full chart, our normalized data set allows us to make more impactful statements. And with that, we have concluded Chapter 12's content on solving environmental problems. Thank you all for being here.